Let's get to today's program. We have blast design requirements, an overview. This is the program description and our learning objectives for today. Also, the continuing education credits you'll earn, 1.0 for PDF and 1.0 AIA LUHSW. Our provider statement as required. Today's giveaways, we have the code TMS 402-602-2016, and we also have a reversible jacket, windbreaker, compliment to the Mason Contractors Association. Chartered in 1896, the Mason Contractors Association of St. Louis is one of the area's oldest construction industry trade associations. So there'll be a little plastic box making its way around. If you want to take a chance on that, put your name or business card in that box and we'll draw at the end. Today's sponsor is Lee May Concrete Block. Since 1947, Lee May Concrete Block has been providing residential and commercial customers durable and functional masonry building blocks for a variety of projects. Do we have Mike Buckley here by chance anywhere? No, but we thank them so much for our refreshments. Thank you. So today's program, we have Hani Hanna as our speaker. Mr. Hanna has over 32 years of experience in structural engineering, project management, and leading large teams in the various aspects of the engineering and construction community throughout the United States and abroad. Mr. Hanna holds a master's degree in structural engineering from Southern Illinois University, Edwardsville, and a bachelor's degree in civil engineering from Cairo University. Mr. Hanna is a registered professional engineer in 27 states and a structural engineer in 3 states. Mr. Hanna was a former member of the Structural Engineering Certification Board. Mr. Hanna currently works for the United States Army Corps of Engineers, Kansas City District. He led the $1.7 billion new National Geospatial Intelligence Agency headquarters project for the federal government, which is the largest federal investment in the Midwest and the state of Missouri. Mr. Hanna occupied numerous positions throughout his career as a chief of design and construction, senior technical lead for the government, former structural engineering manager for Jacobs Engineering, and other supervisory positions in the private sector. Mr. Hanna is an adjunct professor at Southern Illinois University, Edwardsville, teaching advanced concrete design, steel design, and other undergraduate and graduate classes. Please welcome Mr. Hani Hanna.
Thank you. Thank you, Margie. Thank you, everyone, for coming in. Audio check. Am I coming in clear in the back? All right. First of all, we have an Army Chief Warrant Officer in-house, so I'd like to thank you and thank you for your service. Let's give him a round of applause, please. All right. So we've got about 2 hours worth of material to go through in about 50 minutes. So let's go straight into our presentation. Again, this is going to be a blast design requirement and overview. It's just a high level of the requirements of why we do what we do from implementation of the requirements from a federal government Department of Defense standpoint. The first question that would come to mind is why do we need to consider blast effect in any of the DoD owned facilities in the US or OCONUS outside of the United States? Well, if you are doing any government project, any federal project, you will probably get to consider blast effect. If you're in a private sector doing commercial work, you might not necessarily need to consider it. So that's something to keep in mind. If you are involved in any government project under the Department of Defense or any agency under the Department of Defense, you do need to consider the blast effect. We did have in the federal government some criteria. However, this criteria changed due to recent events One of the most significant one, what you see here on the screen, is the Mora Federal Building. The Alfred Mora Federal Building was a United States federal government complex in Oklahoma City. In 1995, that building was a target of a bombing by terrorist Timothy McVeigh. If some of you lived to live this incident, I definitely remember it very well. This incident came about 2 years after another bombing in the World Trade Center. There was a blast in the parking garage under the World Trade Center in 1993. This was a massive explosion. Unfortunately, it killed 168 people. This event was the deadliest act of a homegrown terrorism in the US history at that time. So it was very significant, and it definitely opened the eyes of the federal government on the requirements on designing and protecting federal facilities. Another incident that took place that was overseas is the Khobar Towers bombing. This was in Saudi Arabia. You can see the extent of the damage to this building on the screen. The Khobar Towers bombing was a terrorist attack on part of a housing complex in the city of Khobar, Saudi Arabia. It was a massive explosion that was felt 20 miles away in a nearby small country called Bahrain. It's unfortunate that it took lives, and about 19 American airmen were killed in this event, and almost 500 people were injured and wounded, mostly foreign nationals and Saudis. So those events, even though there were other events around the world targeting US territories and facilities, but the federal government started to take a dive on the requirements that we currently have or what we had at that time. And that triggered a DoD Directive 4270.5, military construction. There were other guidelines out there dated back in 1978 and 1982, but that new directive, based on the new research that the government started to focus on, they renamed 4270.5 to be military construction, or MILCON. You will find all these directives on the website that is on that screen. You will have to, I don't know if you can see my pointer, you'll have to go to this website, create an account. If you're a federal employee, you can access all of those directives using your CAC card. Basically, what this new directive did is it established new policies, responsibilities for military construction programs. We're just going to call them MILCON for the sake of this presentation. And it delegated statutory authorities and responsibilities related to MILCON. It reissued, renamed the previous directive that became obsolete, and it consolidated information previously contained in other directives, and it canceled the 1315.6 directive. You can see that those previous directives, some of them are for like the Air Force overseas and for DoD emergency contingency and other unprogrammed. So they try to combine all of those things and make it more clear on the new requirements that we need to design for. Again, this is something that the DoD started to focus on after those frequent bombing incidents targeting US territories and facilities around the world. The Unified Facilities Criteria, what you see here on the screen, we call them the UFCs. This reference came about after the DoD effort and the Directive 4270.5. This is the DoD minimum anti-terrorism standard for buildings. The UFCs prescribed by the MIL standard 3007. They provide planning, design, construction, sustainment, restoration, modernization, anything that is applicable to the military departments, defense agencies, DoD field activities. All of these will be in accordance to the DoD Directive 4270.5 military. There is a website on the screen. This is the WBDG website. If you go under that website, you can download all of the UFCs. There's multiple of them. And we pretty much have a UFC for everything related to construction, design and construction for military construction. So you need to be familiar with it if you are doing federal and government projects. The preparing authority for the publications, the UFCs, are the U.S. Army Corps of Engineers. They are the preparing activity, of which I work for one of their districts. There are multiple districts for the U.S. Army Corps of Engineers. I work for Kansas City District. The Naval Facility Engineering Command is another preparing authority, NAFAC, and AFCAC, the Air Force Civil Engineer Center. All those three agencies, they joint effort, and they come up with all of the updates to the UFCs. We're going to be focusing today on the DoD minimum anti-terrorism standard for buildings. That is UFC 4-01001. The date of issuance will be on there, and you notice that there's a change too. So we constantly revise and update those references, and every time change comes out, it supersedes the previous change. So make sure that you are using the latest version of the UFC that is applicable to your project. Now, obviously, you have to truncate those revisions at a certain point of your project design. So let's say at 35%, you're going to say, I'm going to be using change 2. By the time you get to 100% CDs, change 3 might be out, right? So at some point in communication with the agency you're working for, you have to make that decision early on to truncate tracking those changes down. When you go into the UFCs, you're going to see that the change number is actually noted, so it's easier to track what changes that took place. So you'll see like a forward slash and then the number 1, that's change 1, or forward slash with a number 2, that's a change 2. So we're constantly changing, revising, implementing new information to the standards. The UFCs are effective upon issuance, so you're not going to get necessarily a notice, but once they are issued and they are on the website, the whole building design guide website, they are enforceable. Now, I call them codes because your structural engineer will probably have to list the number of codes that he's using for the building design. So question, how many architects in-house? Can you raise your hand? Okay, good, because it's an architectural series seminar. So we're not going to focus much on the math behind the blast, but again, this is an overview of all of the requirements that came out of that directive for U 70.5 and the DoD minimum anti-terrorism standard for buildings. The UFCs will be used for all DoD projects, and they work for other customers where appropriate. That includes all construction outside of the United States as well. So change 2 for the UFC added that the United States and its territories and possessions. Now, there are other publications that govern the design if you're doing OCONUS projects. OCONUS is outside the continental United States. That could be the Statutes of Force Agreement, the SOFA, the Host Nation Funded Construction Agreement, the HNFA, and in some instances, a bilateral infrastructure agreement. So you're going to have to be in compliance if you're doing work outside of the continental United States with all of those 4 references, the UFC, the SOFA, the HNFA, and the BIA. Again, as I had mentioned, those are living documents, so it's like a moving target on you. So you always have to keep an eye on the WDBG.org website noted on the screen. So back to the Kobar bombing that I showed you the second picture in Saudi Arabia. One of the findings in the 1996, and that took place in 1996, some of the findings in the Downing Commission report on the Kobar Tower bombing in Bahrain, Saudi Arabia, that there were no standards for force protection in fixed DoD facilities, meaning that we didn't really have a baseline to design and be uniform from a force protection standpoint. So the initial version of that document, the DoD Minimum Anti-Terrorism Standard, was published as an interim in 1999. So keep in mind the three major incidents were the bombing in '93, World Trade Center, the bombing of Oklahoma City, Federal Building in 1995, and the Cobalt Towers in 1996. So it took us, 3 years to issue an interim in 1999, and we finally put it out there as an enforced law in 2002. Fiscal year 2002 programs were all abiding by the DoD minimum anti-terrorism standards for building. Now, why we do what we do, so it's a little different than commercial work, right? So when you're designing a building in a private sector or commercial, you're self-conscious about the cost, right? Economy is a big deal, the budget, the construction cost. But what this standard is doing is actually trying to establish minimum engineering standard that incorporates anti-terrorism based mitigating measure with no identified threat. Well, what does that mean? That means we're trying to cover a full spectrum of threat that we don't know about. It is not defined. But we're trying to envelope a bunch of threat levels and come up with a minimum standard. But why do we do that? Because we want to save lives, right? We want to minimize mass casualties. That is the intent and the purpose of those standards. So you can't put a cost to a human life, right? So what we can do, because we don't have a defined threat per se, is to establish a baseline or a minimum standard of practice that would minimize the loss of life and mass casualties. Again, the intent of those standards is to reduce collateral damage, and we've seen a lot of those in recent years, and also reduce the scope and the severity of mass casualties in the event of a terrorist attack. If you apply those standards, you will probably provide a cost-effective, implementable, and enforceable construction standard to protect personnel against terrorist attack. Now, this is not like an open checkbook, right? So the government doesn't, or the DoD doesn't have an open checkbook. So we understand that while complete protection against all potential threats for every inhabited building, there's a lot of buildings owned by the Department of Defense or the government, is cost prohibitive, but the intent of those standards can be achieved through prudent master planning. So we can apply a few things as we're designing our facilities. Master planning, real estate acquisition, design and construction practices. Now there is an exemption in the standard, so parking garages. A standalone parking garage is exempt from those standards. However, if you do have a parking garage underneath a building, inhabited building, that you have occupant above, the standard applies, okay? If you have, let's say, a parking garage as a rooftop on top of a building that is also an inhabited building, then the standard will apply. So you tie this exemption to the design and construction practices. Now you start to think of, how am I going to master plan my entire complex, right? Do I really want parking underneath the building? Probably not. What if it's unavoidable? Then you apply those standards, right? If we look at the security engineering UFC, so there's a UFC called Security Engineering UFC. We look at two stages, so I'll move to this side so you guys don't feel like you're left out. So we have two phases, right? We have the planning phase and we have the design phase. This flow chart kind of helps the designer guide the way. So first you have to define your design criteria using the UFC 4020. 4020 is the security engineering UFC. 4010 that we mentioned is a design for anti-terrorism. So you ask yourself, only DoD minimum standard required. Is it a yes or a no? If it's a yes, you apply your minimum anti-terrorism standard for buildings, 4-10. If it's a no, you have to go to the Facilities Planning Manual and the UFC 42001, and you abide by those design strategies. Either way, you have to incorporate whatever decision you make into your design strategies, into the planning documents, and then you move down to the design phase. You validate all of your planning requirements, and you go through the same process flowchart. Do I really need to consider minimum practice standard requirements, yes or no? And then you eventually incorporate the protective measures in your design. This is the initial way of knowing which way to do, and then you move into your construction and so on and so forth. If I take a snippet of what defines a level of protection, or what does that mean to you as an architect? Well, if we just to compare level of protection, so we start with below AT standards. AT is anti-terrorism. So below standards means you're doing nothing. You're not protecting anything, right? So you expect severe damage. And if I go all the way up to a high level of protection, let's take a look at the impact. This is a potential building damage performance category. This is your potential door and glazing hazard, and this is your potential injuries. So let's say, for the sake of comparison, if I'm doing very low level of protection, my building itself will experience heavy damage. Probably structural collapse, but not progressive collapse is unlikely. Space in and around the damaged areas will be unusable. Let's look at your glazing and doors. Glazing will fracture, come out of frame, likely to be propelled into the building, potential to cause serious injuries. This is bad, right? This is not the intent of the standards. However, some facilities with low importance on an installation might fall under low level of protection. Doors will become dislodged from the structure, will not create flying debris hazard for category 4, for example. Now let's look at the injury level. Majority of your personnel in the damaged area will suffer serious injuries with potential fatalities. That's what we're trying to avoid. As you go up the chart, if I do a high level protection, I only have superficial injuries are likely for your personnel. The building itself will experience minimal damage, no permanent deformation. The facility will probably be occupied immediately. And look at your doors. Doors will be substantially unchanged. That's what you want. You want people to get out of the building, right? Now, I'm not saying that you're going to design for high level of protection right away, because it might not be required by the agency you're working for, because it's going to cost you a lot of money. So you do want to know exactly what level of protection you're designing for. The criteria, similar to like tornado criteria and earthquake impact to structure and occupants, for glazing and doors, they come out of ASTM F2912 or 2247 and 2927, which are listed here on the screen. So back to the philosophy. Those protective measures are what? They are engineering solutions. To do what? To lessen the risk of mass casualties and collateral damage resulting from a terrorist attack. Again, let's not forget the intent and the focus of those standards, right? We're trying to lessen the risk of mass casualties and collateral damage. The implementation of the standards, what we found out in recent applications, that it will provide some protection against a wide range of threat. Again, we can't read the minds of terrorists. We don't know how much explosion they're going to use. But those standards covers a wide range of threats that if you were to apply the standards, most likely will save lives. Now, obviously, the cost, and it goes without saying, human life is the most valuable thing that when we design from an architectural standpoint and engineering standpoint, it's all about life safety. So cost here is not necessarily the issue. As long as you define the level of threat, you have to apply all of the standards to it. There are two key elements that you would want to consider is time and design practices. Time means you have to put these standards in place ahead of the terrorist attack, right? Otherwise, you defeat the purpose. Meaning you apply it during design and construction. you need to be one step ahead. Design practices is something we need to, again, if you're involved in federal government projects, any federal, any DOD, any IC, intelligence community agencies, you're going to have to keep design practices in mind from the planning stage, from a master planning standpoint. Some of the design strategies is to prevent building collapse, minimize hazardous flying debris, provide effective building layout, limit airborne contamination, and provide mass notification. So if I was to focus on a few of those, let's say prevent building collapse. There is a provision to do progressive collapse analysis on structures 3 stories or above. And we'll talk about this a little bit, but not in depth. This is an architectural series, not an engineering series. So I'm not going to bore you with equations. But something we do in analysis which would prevent progressive collapse, minimize hazardous flying debris. We found out from recent studies from latest blast events that actually most of the injuries came from flying debris from ceilings, from partitions, from glazing, windows, from other features in the building that is what we call non-structural components or architectural features. So, what can we do to as an architect to minimize the hazardous flying debris? If I look at glazing, for example, windows, how many architects like to put a lot of windows in buildings? I should see a lot of hands, right? But when you apply those measures, now you're going to start to think, I actually need to minimize the number of windows. I actually need to maybe scale my window size down, right? Of course, there's design measures to reinforce glazing and have additional reinforcement. That's a whole different story. But from a flying debris standpoint, those are the things that you're going to have to start considering, even though it might not be a standard practice in your office. But those are the measures as a design strategy to consider. Effective building layout. Would you orient the building long way along the street versus 90 degrees to the street? We'll touch on this a little bit down in the presentation because the vehicular threat as a moving vehicle with a target in there can change the criteria based on the building layout on the site itself. Airborne contamination. What can we do with our HVAC system to mitigate or provide some mitigation to limit the airborne contamination, as in potential chemical, biological, radiological agents being distributed throughout the building from the ductwork. So you're going to have to engage with your mechanical engineers expert and see what can we possibly do as an effective design of our HVAC system to minimize the contamination. Building mass notification, you need to let the people know, obviously, that there is a threat and to get them out of the building very quickly. All right, the standard 410.1 talks about standoff distances. The standoff distance is prescribed in the standard, and I'll explain this a little bit. So the heavy shaded square here is your inhabited building. That's your structure. What's around it is what we call the unobstructed space. We need to maintain minimum of 33 feet of an unobstructed space. If this was on an installation, I have this phantom dark line here is installation perimeter. This zone between the unobstructed space and the installation perimeter, which we call the inner clear zone. There's an outer clear zone if you have a perimeter as well at the outer clear zone. So the standard says I need 20 feet minimum standoff distance between the installation perimeter and the unobstructed space, and I need to maintain as a minimum aggregate distance of 50 feet to the outer clear zone. So what does this leave us here? 50 minus 20 is what? 30 feet. What if I have only 20 feet in the outer clear zone? What am I going to do? I can't do it. I can't maintain 20 feet minimum standoff distance because the aggregate has to be 50 feet. That means your planning here is going to have to change. And that 20 feet has to change to 30 feet, which pushes your building down south, which is not what you were planning for. So now you have to reconsider the planning of it. Here is an example of standoff distance installation perimeter without an outer clear zone, period. You still need to maintain 50 feet minimum standoff distance, 33 feet around the building in the unobstructed space. There is no definition of this distance in the inner clear zone, but you have to, under no circumstance, be less than 50 feet minimum standoff distance. So now you can see that the position of the building itself might affect everything else you're doing around the building. Those standoff distances are noted in few pages. This table is actually a few pages long in the publication. So for the sake of comparison, if I look at very low level of protection versus a low level of protection, we're in the Masonry Center, so let's talk about masonry. Unreinforced concrete masonry. The minimum standoff distance for load bearing, LBs means load bearing, is 80 feet, unreinforced masonry. Now, if I reinforce my masonry wall, it drops you down to 28 feet. So what does the reference tells us is you probably shouldn't use unreinforced masonry, right? Now, if you're in the Midwest or the West Coast, you're probably going to be governed by other things like seismic design, and you're going to reinforce your masonry. If you're in the northern states and you're used to not unreinforced masonry, it will work maybe fine for commercial application. When you come to those standards, unreinforced masonry is not going to work for you. If I look at low level of protection, let's look at my 80 feet for unreinforced masonry. That didn't change. My reinforced masonry, that didn't change. So it actually captures two levels of protection. Now, one might ask, well, why do I need to do masonry? Well, can I just do concrete? If you're in a region where they're promoting concrete over masonry, you're not really gaining much. So 6 feet of standoff distance is not much in a master planning site plan. You're actually gaining maybe a couple feet of non-load. NLB means non-load bearing. So masonry performs well in comparison to concrete. Keep in mind that these tables are based on, or the snippets here, based on 55-pound TNT charge. Obviously, this will change. Another comparison level of protection is medium versus high. Again, if I look at reinforced masonry, it's 224 feet. That went up, right, from 28 feet because of the level of protection. This is not hard to achieve if you're a green site, okay, project or installation. It's about the same number for high level of protection. If you look at reinforced concrete, about 276 feet versus 224. Again, I think reinforced masonry will perform very well for you. Now, on a side note, you don't need to probe into the design parameter for the explosive. Okay, how many pounds of TNT? If you don't need to know. So there is a need to know basis, okay? There are certain elements of the design team that will have access to this, and they will do the analysis. So if you don't need to know, don't ask the question, all right? And you have to have certain clearances too. So if you don't have, top secret clearances, you're not gonna be able to find this information. All right, the standard addresses few elements aside from what we discussed already. So concealment, trash containers, electrical, mechanical equipment. So every aspect of your project has a reference in the standard, and you have to be familiar with it. Walls and screens, enclosures, parking within unobstructed spaces. You can actually have parking in an unobstructed space for as long as the explosive device can be seen by someone, okay? So you have to plan your parking for that. Adjacent existing buildings, let's say you're putting a new facility next to an existing facility that doesn't have to abide by those standards. you still have to maintain the 33 feet minimum unobstructed space, which means you might modify the existing parking lot, the existing, let's say they have a trash enclosure you're going to have to remove. There are certain things you still have to maintain. The standards, I think, dropped off of the drive-up, drive-off areas. Those were canceled out of the new standard, and access roads were also deleted. Parking beneath buildings or rooftops, we kind of touched on this. If you don't need to put parking underneath buildings, don't do it. If you have to put buildings or cars parked on a rooftop, we have to apply what we call ACP design, so access control points, where you're actually searching people coming in. Everybody's authorized to be on the installation. So we can do certain measures, but parking underneath buildings are not necessarily the first choice when it comes to those standards. I want to show you a couple videos of a simulation. This is a 3D analysis, finite element analysis, just from a visual standpoint of a progressive collapse resistance simulation. The progressive collapse publication itself is a UFC 42303. We'll see if this video will play for you. This first image here is basically a blast impact on a single column simulation. It's going to play another video, non-related. So this is actually from the Navy. So don't pay attention to this. I want to show you the next simulation for progressive collapse. So are you guys enjoying this so far? Show of hands. All right. All right, there you go. So this is a 3D simulation of progressive collapse on the side of a building here due to an explosion, for example. Here's another example. Your expert in protective design engineering, he's going to be a sub-consultant. He's going to be doing all this stuff and advise the design team of what needs to happen. Let me show you another one. Might be very recent to you guys. So this was a Champlain South Tower collapse in South Florida. This is not necessarily a terrorist attack impact, but I wanted to show you the simulation of progressive collapse modeling in a finite element analysis model. This one has sound to it, so that's good. So that's what we're trying to prevent, okay? So the standards has provisions and how do we bridge, okay, a missing column after a blast event. Here's another image of a collapse that we're trying to prevent, right? All right, I think you guys got the idea. All right, so let's talk about masonry. So standard 9, exterior masonry walls, all right? So we talked about unenforced masonry walls that are not very good in those applications. They are actually prohibited for the exterior walls of new construction that requires to comply with the standards. The masonry walls, exterior walls, must have vertical, horizontal reinforcement distributed throughout the wall section. There is a prescribed percentage for reinforcement. So vertical needs to be at least 0.05%. Spacing is 48 inches on center. And you need to have reinforcing within 1.3 feet of the ends of the walls. Now, why don't we just say 16 inches on center? Why is it 1.3 feet? Because it's a conversion of 410 millimeters. So the federal government uses metric and and all other things, right? So 1.3 is 16 inches in center. So you have to have that. For horizontal reinforcement ratio, it must be at least 0.025%. You can put joint reinforcement no more than 16 inches on center. You can do a bond beam with reinforcement no more than 4 feet, 48 inches on center. Again, with reinforcement at 16 inches from the top and the bottom of the walls. Cavity walls come in play as well, and exterior unreinforced clay concrete or stone masonry as well. So you could use different width of reinforcement as a wall section, but the reinforcement requirement is only on the inner width. Okay, so if you have brick and other things, those requirements are only applied to the inner wall. If you are doing, obviously, work outside the United States, you're using European masonry walls, you're going to have to consult your PDC technical folks on that to see if they are considering this type of material. If I look at the conventional construction parameters, quick comparison here, table EC-5 between reinforced masonry and unreinforced. You're going to need to use blocks 8 inches to 12 inches versus 6 to 12 for unreinforced, obviously, because I can't reinforce double reinforced at 6-inch block. More often when you detail these walls, you're going to end up maybe with double reinforced masonry. It's near hard, not impossible, to put it on a 6-inch wall. The parameter here is a one-way flexure. SS here means simple span. The supported weight is 10 PSF. This weight is not the self-weight of the masonry. This is weight that is attached to the masonry wall. And the minimum block is 1,500 PSI. I think now, by default, we'll get 1,900, we'll get 2,000, we'll get 2,500. So it's not going to be an issue for you. And the minimum density is 120 PCF, which is medium weight concrete. Let's look at the primary threat in a stationary vehicle. Okay, the primary threat is located along a secured perimeter line. So if I was to explain this real quick, so this is your street, this is your standoff distance here, and this is your inhabited building. The truck is parked full of explosives. They set it up. It causes a hemispherical shock wave. This color-coded shock wave is the reflected pressure, and we'll talk about that in a few slides. And then we will have overpressures and drag forces all around and all 4 sides of the building, really. So we're trying to take protective measures against this instance by even having different layers of protection. So you might have a bollard system or things like that ahead of getting to be parked in front of the building. One way to do that is to use pre-tested bollard systems. So those are DoD approved and tested details that you can go and find and use. This is an anti-ram bollard system to protect against moving vehicles attack. There is certain criteria for how many miles an hour you consider for design. So if you're parked parallel to a building, that's 30 miles an hour. If you're parked, if you're at the intersection or a corner of a building, is 50 mile per hour is the velocity, and obviously the car weight will be different. Another type is the anti-ram knee wall. This is a significant concrete barrier wall. It could go up to 24 inches thick with heavily reinforcement in there. So those are details that you can find and use. This is out of FEMA 427. A secondary threat is sometimes considered is a hand-carried weapon placed directly against the exterior envelope. This can be carried in a briefcase, backpack, or any sort of things like that. Now, if you have a pre-screening to the installation, you can detect those. But if not, here you can see the impact or the difference if you were to use 500-pound TNT versus 5,000-pound TNT, for example. Your pressure goes up from 1,600 to almost 4,000. This is the incident pressure plot against the range in terms of PSI. What's good about this, if there is anything good about this, is that the wave pressure actually decays very quickly, okay, versus earthquake, which is more cyclic. All right, explosive pressures. Let's talk about that for a second. They are typically much greater than other loads. All right. Again, fortunately, they decay extremely rapidly. For blast-resistant design, the most significant feature of explosion is a sudden release of energy to the atmosphere. All right. So it's a release of energy above the air pressure, atmospheric condition, and that what causes the most destruction. So let me explain this graph real quick. So there's an explosion device. They set it off. It causes a peak incident pressure, which is above atmospheric pressure. And it tries to die off very quickly. However, when it hits the building, it actually amplifies, okay? We call this the peak reflected pressure. It reflects with a reflection factor C sub R, R is for reflection, and it almost doubles, right? So we get an amplified peak reflected pressure, and then the reversal between positive phase duration and negative is that rebound, okay? That rebound from that pressure, it's not a reversal of load like seismic, for example. It's actually a rebound of the building walls that causes a negative pressure, and that's why you see in that graph we're going below the atmospheric pressure line if this was to be an atmospheric line. So this is time versus peak pressure, just so you understand this, this graph. I didn't plot it here, but there's an impulse curve as well. Impulse curve is the integration of those curves. Okay, if you take the area under a curve, that's the impulse pressure. That you're going to hear that term quite a bit. Let's look at the effect of shock wave expansion and engulfment of buildings. The first image here, blast wave breaks windows, exterior walls blown, columns may be damaged. And then it goes into the floors are actually moving upward. And we move into full engulfment. So you got damage on all four sides, columns bowing in, floor losing columns, floors are moving up, and so on and so forth. Progressive collapse, let's touch on that real quick. Designed for buildings for progressive collapse. Obviously, a risk category is a key here. So you have to know which risk category you're designed for. And based on your risk category, you have options. You either do the tie force or the alternate path method, or both, or enhancement of local resistance. So it's very key to engage with your consultants ahead of time, because this makes a big difference in the design analysis. What we're trying to achieve with the tie force method is to create peripheral ties in the horizontal diaphragm. So this is your floor plate, and the red arrows are your peripheral ties. We're also trying to achieve a vertical tie at the columns and introduce internal longitudinal and transverse ties. Those are the blue arrows on the screen. What we're doing is we're tying the structure together. Okay, we don't need a weak link in our structure. This also, something interesting about the previous slide. This works great for uniform loaded floors, but more often your floor load is not the same. So you have to consider sub areas, and every sub areas will also need to be designed for those internal ties and peripheral ties. When it comes to a heavy loaded, which is the shaded zone here, and the lightly loaded floor areas, those dashed green lines here, those peripheral ties, internal ties, needs to be designed for the sum of the forces, okay, from the lightly loaded and the heavily loaded. Of course, every floor will have an opening, hopefully not from an ATFP standpoint, but it's inevitable that you have to have floor openings. So there are also criteria on how to anchor those ties together in your floor design diaphragm. There are certain zones that you can do mechanical splices, welded splices, and Class B lap splices. So it gets very intense in detailing when you consider progressive collapse tie force method. Example of what controls your design is noted in this table. The most important thing is your connection. You don't want your connection to fail. So the controlling load, whether it's deformation or force controlled, is your PVM. And for architects, P is axial load, V is shear, and M is moments. So you have to consider the extreme loading controlling action for connections. I should note that, let's move on. So if I move on to the next method, which is the alternate path method, what we're trying to do, let's say this is your building here. I got 3 columns. I'm going to remove one of the columns from the analysis, and I want to make sure that the building doesn't collapse, right? I'm preventing progressive collapse from happening. What that means is if this bay is 30 feet long, I need this beam to actually span 60 feet in a catenary action. Now, if it spans 60 feet without collapsing, without losing capacity, you did your job. The building's not going to collapse. Will it deflect 2 or 3 feet? Possibly. But what does that mean? I'm not comparing it to Elevator 360 or Elevator 240, right? I'm just trying to make sure that the building doesn't collapse and occupants have enough time to evacuate. Here's an equation for increased gravity load. I'll leave that for the engineer series, I think. We get some of these factors when we do alternate path method. There is amplification factor called omega, whether you do linear static analysis, which is the upper table, versus dynamic nonlinear, the omega factor is changed. So if we look at the masonry, for example, load bearing, you're amplifying the load or that load combination by 2. So you're doubling the loads. Enhanced local resistance. This is the third level of consideration next to the tie force and alternate path method. What we want to do, make sure that the two components must meet the ELR requirement, enhanced local resistance, are your columns or walls, connections between the ends of the walls to the lateral support, which is your floor plate or base plate. If I was to focus on chapter 6, that's your masonry chapter, this chapter provides specific requirement for design of masonry buildings to resist progressive collapse. There's a lot of conditions related to material properties, overstrength factor. You're going to have to start using ASC 41. So that's another publication that structural engineers would be using. Reduction factor fee for masonry. Components have to be capable of carrying. So the takeaway of this is the rotation capacity, the 0.2 radiant, which is 11.3 degrees. That's what we're trying to achieve, okay? If I can get capacity with a rotation of 0.2 radiant or less, then I meet the standards. If you exceed it, it's a trial and error. You have to redesign the element. Tie force method requirement is also applicable to masonry. Alternate path method for masonry is also applicable. Modeling and acceptance criteria. This is in chapter 11 of ASC 41. And enhanced local resistance requirement for masonry. You also have to apply it according to section 3.3 for load-bearing masonry walls buildings. Let's look at detailing here. So if you go to this website, the ncma.org website, you're going to find a lot of information. This is Tech Note 1421A. Shear response modes for masonry walls, basically how do they fail, right? We either fail them in direct shear, so the wall just literally breaks in a horizontal fashion, or a diagonal shear. So you can see that shear mode here, kind of a diagonal break. Those are the two modes of failure. Obviously, we're going to have heavily reinforced masonry walls to help us mitigate that. From a detailing standpoint, if you look at this is a plan view of a masonry wall, what the standard will require you to do is to fully grout your wall. So partial grouted wall isn't going to be good enough based on the testing we've done, because that also creates a flying debris in the ungrouted cells. So you have to fully grout, whether you have bars in every cell or not, but the standard will most likely require you to do it with a stirrup, okay, that horizontal tie. You could also have a doubly reinforced, they call it doubly reinforced layout, even though you have staggered bars. So there's one here and one here in a staggered fashion. We call that doubly reinforced with one vertical bar, and this is going to be a closed tie. Or you can literally put 2 bars in every cell with a closed tie. Now you know why most likely you're going to end up with a 12-inch block wall, right? If 8-inch can do the job for you. Certainly not a 6-inch block. Based on testing, we tested 2 walls, unreinforced with joint reinforcement and reinforced masonry walls, and you can see the difference here. The unreinforced masonry walls are very brittle. There's no ductility there. They fail terribly, miserably. They are prohibited in use. Reinforcement certainly does the job. It does fail whether it's a horizontal shear or diagonal shear. So again, the takeaway of today is reinforce your masonry walls, okay? Don't use unreinforced masonry. Some of the design and construction challenges that we found outside of the masonry world, if you will, is doors, right? So doors from a life safety would want to swing which direction, in or out? In or out? We want our doors to swing out from a blast standpoint also, right? We don't want any doors to swing in because that's a flying debris, right? So keep that in mind. Some doors might swing in some of the office buildings, sometimes, right? If you're in an office space, that door swings in. Well, that's a flying debris. You ultimately want, but it's hard to achieve. So we have some issues in the industry to solve these things, right? Through door hardwares, latching devices, uh, masonry blast walls. They have to be 8 or 12-inch block, fully grouted. Penetrations on those walls are very challenging. You can't have too many penetrations through a masonry wall when it's based on those standards. There is a strong difference between blast requirement and ballistic requirements, and that's a whole different topic for a different day. Here's an image or a picture of what a blast door looks like. This is definitely not your hollow metal door, right? This is not something you buy from Home Depot. Here's a double door blast door. So there are things that you need to start to probe into if you're getting yourself into projects like this. I wanted to show you here a comparison between a blast load and a seismic load. Very quickly here, explosion are single high pressure impulse. They act over milliseconds. Your seismic are vibrational load. They act over seconds. This is directly on the exterior envelope. This is the base of the building, and so on and so forth. The most significant difference is that the mass actually helps you from a blast standpoint to resist the explosion loads versus it works against you if you're doing a seismic design. So some of the differences, I'm sure there are more. Those are the ones I wanted to share with you. Another image here, just from a visual standpoint, a blast event, it engulfs the whole building. Seismic is really a ground motion below grade. The blast impulse here decays very quickly versus cyclical load from a seismic standpoint. The blast event might take a good portion of that building, like the Oklahoma City bombing. And seismic is really a global performance of the entire building, shaking back and forth. I gave you some of the references that we discussed and the names of every UFC here, so you can track it back when you go back to your office and start to dig into all of those UFCs and others. And there are some commercial softwares out there, like SBEDS and BlastX and others, that will do those blast effect predictions and performance of structures that your consultant will probably be doing. Again, it's on a need-to-know basis. If you don't need to know, don't ask the question type thing. I do have a video to share with you, and then we'll take questions. So let's see if I can pull up that video.